Image formation by concave lens. There are only two possibilities of position of object in the case of a concave lens. A. Object is at infinity. B. Object is between optical center O and infinity. Object is at infinity. A highly diminished point-sized, virtual and erect image is formed when object is at infinity by a concave lens at principal focus f1. Position of image at f1. Nature of image virtual and erect. Size of image point-sized, highly diminished. Object is between optical center O and infinity. A diminished, virtual and erect image is formed between principal focus f1 and optical center O. Image formation by convex lens. There are 6 possibilities of position of object in the case of convex lens. Object at infinity. Object beyond center of curvature C. Object at center of curvature C. Object between center of curvature C and principal focus F. Object at principal focus F. Object between principal focus F and optical center O. Convex lens converge parallel rays coming from object at infinity and a highly diminished point-sized real and inverted image is formed at principal focus f2. A diminished, real and inverted image is formed between principal focus f2 and center of curvature c2 at the opposite side when an object is placed beyond c1 of a convex lens. A same-sized, real and inverted image is formed at center of curvature c2 when object is placed at center of curvature c1 of a convex lens. An enlarged, real and inverted image is formed beyond center of curvature c2 when an object is placed between center of curvature c1 and principal focus f1 of a convex lens. An infinitely large, real and inverted image is formed at infinity when object is placed at principal focus f1 of a convex lens. A virtual, erect and enlarged image is formed at the same side of lens when an object is placed between principal focus f1 and optical center O of a convex lens.
Image formation by concave mirrors. The method of locating the image produced by a concave mirror consists of drawing light rays emanating from key points on the object and finding where these rays are brought to a focus by the mirror. This task can be accomplished using just 4 simple rules. An incident ray which is parallel to the principal axis is reflected through the focus F of the mirror. An incident ray which passes through the focus F of the mirror is reflected parallel to the principal axis. An incident ray which passes through the center of curvature C of the mirror is reflected back along its own path, since it is normally incident on the mirror. An incident ray which strikes the mirror at its vertex V is reflected such that its angle of incidence with respect to the principal axis is equal to its angle of reflection. Consider an object ST which is placed at a distance P from a concave spherical mirror. For the sake of definiteness, let us suppose that the object distance P is greater than the focal length F of the mirror. Each point on the object is assumed to radiate light rays in all directions. Consider 4 light rays emanating from the tip T of the object, which strike the mirror. As shown in the figure, it can be seen that the reflected rays all come together at some point T1. Thus, T1 is the image of T. As is easily demonstrated, rays emanating from other parts of the object are brought into focus in the vicinity of T1 such that a complete image of the object is produced between S1 and T1. This image could be viewed by projecting it onto a screen placed between points S1 and T1. Such an image is termed a real image. According to the figure, the image is inverted with respect to the object and is also magnified. This figure shows what happens when the object distance P is less than the focal length F. In this case, the image appears to an observer looking straight at the mirror to be located behind the mirror. For instance, rays emanating from the tip T of the object appear, after reflection from the mirror, to come from a point T1 which is behind the mirror. Of course, the image behind the mirror cannot be viewed by projecting it onto a screen, because there are no real light rays behind the mirror. This type of image is termed a virtual image. The characteristic difference between a real image and a virtual image is that immediately after reflection from the mirror, light rays emitted by the object converge on a real image, but diverge from a virtual image. According to figure, the image is upright with respect to the object and is also magnified.
Important terms for spherical lens. Center of curvature. The center of sphere of part of which a lens is formed is called the center of curvature of the lens. Since concave and convex lenses are formed by the combination of two parts of spheres, therefore, they have two centers of curvature. One center of curvature is usually denoted by C1 and second is denoted by C2. Focus. Point at which parallel rays of light converge in a concave lens and parallel rays of light diverge from the point is called focus or principal focus of the lens. Similar to centers of curvature, convex and concave lenses have two foci. These are represented as f1 and f2. Imaginary line that passes through the centers of curvature of a lens is called principal axis. Optical center. The central point of a lens is called its optical center. A ray passes through optical center of a lens without any deviation. Radius of curvature. The distance between optical center and center of curvature is called the radius of curvature, which is generally denoted by r. Focal length. The distance between optical center and principal focus is called focal length of a lens.
Image formation by convex mirrors. The definitions of the principal axis, center of curvature C, radius of curvature R, and the vertex V of a convex mirror are analogous to the corresponding definitions for a concave mirror. When parallel light rays strike a convex mirror, they are reflected such that they appear to emanate from a single point F located behind the mirror. This point is called the virtual focus of the mirror. The focal length f of the mirror is simply the distance between V and F, as is easily demonstrated in the paraxial approximation. The focal length of a convex mirror is half of its radius of curvature. The image produced by a convex mirror can always be located by drawing a ray diagram according to four simple rules. An incident ray which is parallel to the principal axis is reflected as if it came from the virtual focus F of the mirror. An incident ray which is directed towards the virtual focus F of the mirror is reflected parallel to the principal axis. An incident ray which is directed towards the center of curvature C of the mirror is reflected back along its own path. An incident ray which strikes the mirror at its vertex V is reflected such that its angle of incidence with respect to the principal axis is equal to its angle of reflection. Two rays are used to locate the image S1T1 of an object ST placed in front of the mirror. It can be seen that the image is virtual, upright, and diminished.
Sign convention for reflection by spherical mirror. While dealing with the reflection of light by spherical mirrors, we shall follow a set of sign conventions called the New Cartesian Sign Convention. In this convention, the pole P of the mirror is taken as the origin. The principal axis of the mirror is taken as the x-axis, x-x of the coordinate system. The object is always placed to the left of the mirror. All the distances parallel to the principal axis are measured from the pole of the mirror. All the distances measured to the right of the origin along plus x axis are taken as positive, while those measured to the left of the origin along minus x axis are taken as negative. Distances measured perpendicular to and above the principal axis along plus y axis are taken as positive. Distances measured perpendicular to and below the principal axis along minus y axis are taken as negative. Snell's law. The light travels at faster speed in rare medium and at slower speed in denser medium. For example, air is a rarer medium than water or glass. The angle between incident ray and normal is called angle of incidence, and it is denoted as I. The angle between refracted ray and normal is called the angle of refraction. Angle of refraction is denoted by R. Laws of refraction. A. The incident ray, refracted ray, and normal to the interface of given two transparent media all lie in same plane. B. The ratio of sine of angle of incidence and sine of angle of refraction is always constant for the light of given color and for the pair of given media. Law of refraction is also known as Snell's law of refraction. Sin I upon sin R is equal to constant. Lenses. Lens is an optical device which converges or diverges the rays of light before transmitting. A lens has similar shape to lentils and genus of lentil is called lens. Thus, a lens got its name after the shape and name of genus of lentils. A lens is made by combining at least one part of sphere made of transparent material, generally glass. Most of the lenses are made by the combination of parts of transparent sphere. Concave and convex lens are most commonly used spherical lens. Lens having two spherical surface bulging outwards is called convex lens. It is also known as biconvex lens because of two spherical surface bulging outwards. Lens having two spherical surface bulging inwards is called concave lens. It is also known as biconcave lens because of two spherical surface bulging inwards. Lens formula and magnification. The lens formula is a relation between the focal length of the lens and the object and image distances from it. This relation is for both concave and convex lens. 1 upon V minus 1 upon U is equal to 1 upon F, where V is the distance of image, U is the distance of object, and F is the focal length of lens. Distance of object and image is measured from the optical center of the lens. The ratio of height of image and that of object, or ratio of distance of image and distance of object, gives magnification. It is generally denoted by M. The positive sign of magnification shows that image is erect and virtual, while a negative sign of magnification shows that image is real and inverted.